Assalamu alaikum wa rahmatullahi wa barakatuh. This video is about solving exercise number 15 in our book. The exercise states that a semicircular rail of horizontal diameter AB equals 2r is placed in a vertical plane. Two particles S1 and S2 of respective masses M1 and M2 such that M1 is less than M2 slide without friction on the inner surface of this rail. Initially, the particles are located as shown in this figure. Let's see what did they give us. AB equals 2r, M1 less than M2, and there is no friction. Part A. Particle S is released at point B without initial velocity. Determine its velocity v1 vector at the lowest point C. To solve this exercise, we have two methods, either using conservation of mechanical energy or we can use the kinetic energy theorem. Since they didn't mention anything about the horizontal plane reference for gravitational potential energy, so we're going to use the kinetic energy theorem. According to the kinetic energy theorem, which states that kinetic energy at C, which is final, minus kinetic energy at V, which is the initial, equals to the sum of the work done by external forces. Half m1 v1 squared minus half m1 v0 squared, where v1 is the velocity at C and v0 is the velocity at B, equals to the work done by mg plus the work done by n, because here we have the weight and the normal as the forces acting on this particle. But initial velocity is 0, so the kinetic energy initially is 0, and the work done by the normal force is 0, since n is perpendicular to the displacement. So we can say half m1 v1 squared minus 0 equals to m1 gr, since this height from B to the ground is the radius of the semicircular rail. Then we can say v1 equals to the radical 2g times the radius r, while v1 vector is tangent to the rail at point C. Now part B. Initially at rest at point C, particle S2 collides elastically with S1. Determine the velocities v1 vector and v2 vector of both particles just after collision. They want us to find two velocities, so we should find two equations of two unknowns. The keys here to solve this exercise are two words, just after collision and elastically with S1. Starting with the idea of collision, remember that in last videos we said that we should start with mentioning the system that we are studying, which is S1 and S2. Then name the forces acting on the system, try to find the result to see whether there is conservation or non-conservation of linear momentum. In part A, we said that the forces acting on B at point C is just the weight and the normal, and so is here when we have the system S1 and S2. The forces will be weight and normal, thus the sum of forces is 0, then linear momentum is conserved. So linear momentum just before collision should be equal to the linear momentum just after collision. Then m1 v1 vector plus m2 v2 vector equals to m1 v1 vector plus m2 v2 vector after collision, but m2 v2 vector before collision is 0 because it was at rest. These velocities are collinear, which means that we can write this equation algebraically as m1 v1 equals m1 v1 after collision plus m2 v2 after collision. Rearranging it where m1 in one side and m2 into the other side, we can write it as m1 into v1 before collision minus v1 after collision equals to m2 v2. This equation will be number 1. Now we need another equation. We said that we should use the given elastic collision. So it means the sum of kinetic energy just before collision is equal to the sum of kinetic energy just after collision. Here we have two particles before collision, then we can write half m1 v1 squared plus half m2 v2 squared equals to half m1 v1 squared after collision plus half m2 v2 squared after collision. And remember that C was initially at rest, then its kinetic energy is 0, and the equation is written as half m1 v1 squared minus v1 squared after collision equals to half m2 v2 squared in the other side. Using the identity a squared minus b squared, we can write the equation as m1 into v1 minus v1 into v1 plus v1 after collision, which is equal to m2 v2 squared, and we reduce the half from the two sides. This equation is number 2. Now we have two equations of the two unknowns v1 and v2 after collision. How should we solve these two equations? We are going to divide equation 2 by equation 1. Writing these two equations like this, we can reduce m1 by m1 and v1 minus v1 by v1 minus v1. On the other side, we can reduce m2 by m2 and v2 by v2 from the denominator. Finally, we can write it as v1 before collision plus v1 after collision equals to v2 after collision. We still have two unknowns, v1 and v2. We're going to name this one as equation 3. Replacing equation 3 in equation 1, after expanding it, we find it as m1 v1 equals to m1 v1 plus m2 into v1 plus v1, where v1 plus v1 after collision is the velocity after collision v2. Remember that we want to find v1 after collision or v2 after collision, and in this equation we have only one unknown, which is v1 after collision. Rearrange this equation to find v1 in one side and the rest in the other side. The equation will be number 4, v1 equals to m1 minus m2 over m1 plus m2 multiplied by v1, which is the velocity before collision. Replacing 4 in equation 3, the answer will be v1 plus m1 minus m2 over m1 plus m2 times v1 before collision equals to v2. Also here we have only one unknown, which is v2. We can find v2 as 2m1 over m1 plus m2 times v1. If we take common denominator m1 plus m2 and solve it, the answer will be v2 equals to 2m1 over m1 plus m2 times v1. Part C, they said, determine the ratio m1 over m2 if both balls reach equal maximum height. To solve this exercise, we should use what we have as givens at mean time. We should find a relation between masses, height, and velocities, because this is the only thing that we have from before. We're going to use the kinetic energy theorem, since it relates the speed in the kinetic energy and the height in the work done by weight. Let's try it. For mass m1, and according to the kinetic energy theorem, we can write it as half m v final squared minus half m v1 squared equals to the work done by weight plus the work done by n. Finally, at height maximum, the kinetic energy will be 0, and the work done by normal reaction is 0 since n is perpendicular to the displacement. So, minus half m1 v1 squared equals to minus m1 g h maximum, since the ball is moving upward, the work done by weight is negative. Then 1 over 2g into v1 squared equals to h maximum 1. The same for m2, and the result will be 1 over 2g v2 squared equals to h maximum 2, and here we have 2h maximum, but they said they will reach equal maximum height. Write them equal to each other, and 1 over 2g v1 squared equals to 1 over 2g v2 squared. Reducing 1 over 2g from both sides, we will find v1 squared equals to v2 squared. Square root both sides, then v1 as magnitude will be equal to v2 as magnitude. But V1 equals to M1 minus M2 over M1 plus M2 times V1 before collision. This one is negative. Why? Because they said M1 is less than M2, while V2 is positive since M1 is positive. Therefore, the equality should be written as minus V1 to be positive equals to V2, which is positive. Now replace the two expressions and make equality between them. Minus M1 minus M2 over M1 plus M2 times V1 before collision, which is minus V1, equals to 2M1 over M1 plus M2 times V1 before collision. Then reduce V1 with V1, M1 plus M2 with M1 plus M2 on both sides. Solve this equation. The answer will be M2 equals 3M1. Then divide M1 by M2. It is 1 over 3. Then the ratio is 1 over 3. This is the end. If you have anything, don't hesitate to ask your teacher. May Allah bless your work.